our dienophile has to have a very specific conformation. This is not a configuration, this is a conformation because of rotation about a single bond, in order to produce the Diels-Alder product. In order for the diene to produce this Diels-Alder product, it must be in the s-Cis conformer. The s-trans conformer cannot react by Diels-Alder unless it can rotate into s-Cis. And if it has a single bond that is capable of rotating, then it can react. Okay, and so what we can actually do is we can rank which diene is going to react the fastest based on what these two groups that cause steric strain are. If they're both hydrogen, that's fine, but what if they're something bigger, like a T-butyl group? Then the chances of rotating into the s-Cis conformer would be less. Okay? In addition, if the diene is part of a ring and it's in the s-trans form in the ring, then it cannot rotate and it's locked in that s-trans conformation, you'll get no reaction. And I've actually seen that on the ACS test, where they present you with a diene in a ring that has the s-trans conformation. Rotation is not possible. And so the correct answer to the multiple choice question is no reaction. Okay, we can have, most of our dienes and rings are locked in the s-Cis conformation. Ring dienes create very unique looking products, which often can confuse students. So we have a new bond for our diene. This is our electron withdrawing group, EWG. And so we have our more positive carbon over here. And that means that carbon 1 of our diene will bond at carbon, at this more positive carbon, and then the more positive, then the dienophile pi electrons go and bond at carbon 4, and the pi electrons between carbons 3 and 4 of the diene move to carbons 2 and 3. What that means is that when you draw the product, you can draw the product in two ways. You can draw it by drawing this angle, then going straight up, drawing a backward line until you get past where you drew your line up, and then connect down, then draw 4 bonds like this, and that will give you, or these 3 additional bonds, that will give you the structure that they showed. Now there's another way to draw this that is also correct, and that is that you can leave your pentane ring as is, potentially drawing it slightly larger, but now carbons 1 and 4 are bonded to two new carbons. Okay, and so what you would have to do is under-exaggerate those new bonds and somehow put them both inside of the ring. And then potentially draw that you have your CO2 group coming out through this line. So you have to decide which way is best for you. You could also draw it, which might be better, with keeping the ring where it is and then drawing a really long bonds to your Dieno file. And the software, if you have to do this in mastering chemistry, the software will count this as correct. Because it is, it's just that we had to make the bonds longer to make the new molecule more obvious. Okay? So I will accept either way of drawing this when you do your Diels-Alder handout. Okay. Note that we have formed two products. These are called bridged bicyclic compounds. One of them is formed in 74% yield and the other in 26% yield. So the position of the electron withdrawing group is what we call endo, or down. So when it's on this bottom bond, it's called endo, and if this hydrogen is on the exo position. And why is that stable is because this carbon has actually this C double bond O is sticking out, as sticking towards the pi electrons between carbons 2 and 3. And the pi-pi interaction is making the energy of the product lower so that it's more thermodynamically stable. So endo is more thermodynamically stable. Okay, so bridged cyclic rings are when we have more than two rings that share two non-adjacent carbons. So they're not adjacent, which means they're not in a 1-2, they're 1-3, 1-4 or more carbons apart. Fused bicyclic rings are when the two carbons shared are adjacent carbons. They're neighbors. Endo and exo products. Endo product is favored when we have a carbonyl group or an electron withdrawing group or pi electrons that can interact with the pi bond. So pi-pi interaction. The exo product is favored if there is a bulky group, like a tert-butyl group, where there's not going to be any favorable pi-pi interaction, but instead we will have steric hindrance. In the case that R would produce steric hindrance, then it will be in the exo position. So usually we only get endo for pi if R has pi bond to heteroatoms. Or to, for example, like for cyanide or such. And we get our exo when R has no extra pi bonds to heteroatoms and R is all sp3 atoms. Okay, stereochemistry of the Diels-Alder reaction. How do we know what if we're gonna make a new racemic mixture, just like in chapter 7 and 6, if our new product contains an asymmetric center, then both enantiomers will be made because we can add from below or above the pi bonds. So if the reaction creates a new asymmetric center, then we will form a racemic mixture. And you have to show that with your wedges and hatched bonds. If the reaction creates two new asymmetric centers, then we will form the cis enantiomers or the trans enantiomers. Okay, so if we have a diene reacting with the cis dienophile, we'll form the cis enantiomers for our products. And if we have the trans dienophile reacting with the diene, then we'll form the trans products. Oh yeah, we don't have Science Saturday, so this slide can be deleted.